Welcome to the third part of oscillations, and in this part you will learn about simple harmonic motion. Simple harmonic motion. Consider a particle vibrating back and forth about the origin of an x-axis between the limits plus a and minus a as shown in the following diagram. In between these extreme positions, the particle moves in such a manner that its speed is maximum when it is at the origin and zero when it is at plus minus a. The time t is chosen to be zero when the particle is at plus a and it returns to plus a at t is equals to capital T, the time period. To study the motion of this particle, we record its positions as a function of time by taking snapshots at regular intervals of time. A set of such snapshots is shown. A sequence of snapshots taken at equal intervals of time showing the position of a particle as it oscillates back and forth about the origin along an x-axis between the limits plus a and minus a. The length of the vector arrow is scaled to indicate the speed of the particle. The speed is maximum when the particle is at the origin and zero when it is at plus minus a. If the time t is chosen to be zero when the particle is at plus a, then the particle returns to plus a at t is equals to capital T, where t is the period of motion. The motion is then repeated. By rotating the figure reveals that the motion forms a cosine function as shown. The position of the particle with reference to the origin gives its displacement at any instant of time. For such a motion, the displacement of the particle from a certain chosen origin is found to vary with time as a function of x with time t, a cos omega t plus phi, in which a, omega and phi are constants, and the graph represents the motion with period t indicated. This one is the reference of the quantities in equation. X denotes the displacement, a amplitude, omega angular frequency, phi phase constant, and omega t plus phi combinedly represents the phase. The motion represented by this equation is called simple harmonic motion. In short form, we will write it as capital SHM. Means the motion, periodic motion, is a sinusoidal function of time. The quantity A represents amplitude. It is a positive constant which represents the magnitude of the maximum displacement of the particle in either direction. The cosine function in equation varies between the limits plus minus 1. So the displacement x varies between the limits plus minus a. A plot of displacement as a function of time as obtained from equation 1 means from x is equals to a cos omega t plus phi with phi equals to 0. The curves 1 and 2 are plots of equation 1 for two different amplitudes a and b. The difference between these curves illustrates the significance of the amplitude. The time varying quantity omega t plus phi in equation 1 is called phase of the motion, and it describes the state of motion at a given time. The constant phi is called phase constant or the phase angle. The value of phi depends on the displacement and velocity of the particle at t is equals to 0. The phase constant signifies the initial conditions. A plot obtained from equation 1 is drawn. The curves 3 and 4 are for phi equals to 0 and minus pi by 4 respectively. And here the amplitude A is same for both the plots. This diagram represents the values of phi corresponding to the position of the particle at time t is equals to 0. The constant omega, called the angular frequency of the motion, is related to the period t. And to get their relation, let us consider phi is equals to 0 in equation 1. So it will become x is equals to a cos omega t. Now since the motion is periodic with the period t, the displacement x must return to its initial value after one period of motion, that is x must be equals to xt plus capital T for all values of small t. Means a cos omega t is equals to a cos omega of t plus capital T. As the cosine function repeats itself when its argument has increased by 2 pi. Means omega t plus capital T will be equals to omega t plus 2 pi or omega t equals to 2 pi. Thus the angular frequency omega will be equal to 2 pi by capital T. And the SI unit of angular frequency is radians per second. The plots of equation 1 for phi equals to 0 for two different periods are shown for the significance of period capital T. In this plot, the simple harmonic motion is represented by curve A, has a period capital T, and that represented by curve B has a time period t dash equals to t by 2.